Hi, everyone. So welcome to our 79th session of MedAI group exchange sessions. So this week with us, we have Tom Hartvigsen from MIT to speak about his work on model editing and preparing. Tom Hartvigsen is a postdoc at MIT and an incoming assistant professor at University of Virginia. He is focused on core challenges in making machine learning and data mining systems responsibly deployable in healthcare settings, mostly for time series data and text. His work has appeared at top venues such as KDD, ACL, NeurIPS, AAAI, and he has also ran the 2022 NeurIPS workshop on learning from time series for health and is the general chair for 2023 Machine Learning for Health Symposium. Tom received his PhD in data science from Worcester Polytechnic Institute in 2021, where he was advised by Elke Rundensteiner and Xiangdan Guang. Thank you so much, Tom, for joining us today. And before we start, do you have any preference on how would you like to take questions? Can we interrupt you in the middle, or do we have specific breaks in your talk for the questions?
Yeah, interruptions are totally fine. I'll also try to take some pauses for questions when it's appropriate.
Thank you. So as always, let's try to make this session as interactive as possible with good audience participation. And without further ado, let me hand it over to Tom.
All right, great. Yeah, so thanks for such a kind introduction. I'm looking forward to sharing some of my work on avoiding model aging by continually editing and repairing deployed models. I'm assuming that if you're attending this seminar, then you agree with me that our healthcare system needs dramatic improvement, but I'll just rehash some key facts that are sticking out with me. Is in the US, we have about 250,000 deaths per year from medical errors alone, which is the third leading cause of death. We have a tremendous number of misdiagnosis injuries in hospitals. We spend an unbelievable amount on our healthcare system, far more than other comparable countries. And physicians are now reporting they spend about 2/3 of their time on paperwork instead of actually working with their patients. And maybe there's hope that this will change with GPT-4, but we'll see. And then across the board, we also obviously experience high care disparities between different groups. And so machine learning has been posed, of course, as an exciting solution to a lot of problems in the healthcare system, stemming from major advances that have happened on the data set size and access and the sources of data that we now have more and more access to and can do active machine learning research on. We're finding that models are starting to behave at expert levels for some specific tasks, largely computer vision and dermatology and chest x-ray models so far are performing extremely well. And then more and more models are actually getting approved for deployment. So there's a growing, accelerating pipeline for bringing models into practice in the US and around the world. But today's systems remain extremely limited. And this is largely because the prevalent machine learning research paradigm is very far from what we actually work with in healthcare, where the prevalent paradigm involves massive clean data sets, the use for relatively low stakes tasks, and then the data they observe or the tasks they're used for don't really shift very much over time. And in this paradigm, we've seen lots of really recent and exciting advances like ChatGPT and DALL-E 2. But in healthcare, we're often sort of dealing with the opposite. We usually have very small and noisy data sets, even though there's lots of data out there, they're sort of spread apart. The tasks we want to use machine learning for are much higher stakes. And of course, the data themselves shift over time, both by being time series and then by the population health changing over time. And so my work is on making machine learning more deployable in healthcare. And I work across the pipeline in a lot of different problems. So for example, working on learning from small and noisy data sets, particularly how do we avoid perpetuating historical bias and dealing with irregular sampling, training models that are effective when used for high stakes tasks and trying to match the criteria of high stakes tasks to the models that we train. And then finally on the deployment side, making models that are more interpretable to use, that behave more fairly, and then end up actually being updatable during deployment so that we can handle more shifts over time. And so today I'm going to talk a little bit about one paper from the deployment category where we're asking how can we edit precise specific behaviors of already deployed models. So when we train our models and we go to deploy them, oftentimes they will misbehave in ways that we didn't expect. So for example, large language models easily perpetuate bias if it is existing in their training data. If you're curious, we have a paper from ACL last year talking a lot about the bias. We sort of use this property of GPT-3 to perpetuate biased sentences against different groups to create a bunch of training data that you can then use to detect more bias in the future. But this is also very prevalent in clinical note data as well, where models can bake in these biases against different groups. And then it's also simply models can make mistakes when you pass in instances that are unlike anything they've seen before. Like, for example, this image is on the right is from a fatal crash from an autonomous vehicle that saw a person walking across a highway at night with a bicycle and didn't recognize that it was actually a person. And then in practice, especially in healthcare, we also see that the accuracy of your models just simply decays over time as the population shifts. And so these sorts of failures happen oftentimes when the environments or the requirements on our models shift. So for example, on the left, we'll see from I think it was in 2021, some folks at the University of Michigan found that the EPIC's sepsis model started severely over-predicting sepsis cases right before the first COVID cases. And then as COVID cases increased and people were starting to get more fevers than expected, they found that the model was relying on these features and started over-predicting sepsis cases. I think it about doubled the prediction of sepsis. And then second, the label distributions that we observe also just simply shift over time. Like, for example, in the center, you can see the rates of diabetes shifting over the years. And so as the label distribution changes, our model is going to have been conditioned on the older, lower prevalence and often then end up under predicting. And then finally, which I'll focus on today, noisy labels can also often be corrected. So for example, on the right is from a paper where there's a bunch of labels collected for some chest x-ray data set. And then later on, they found that a bunch of the labels had been incorrect. And so they wanted to go back and collect higher quality, more accurate labels for the data set. And so this is the case where I want to focus on it today. And again, like just in this example, if the true labels are shifting, but your model was trained on a different label, it of course is going to start failing with respect to this new task. And how do we update that? So I want to walk through a motivating example that is pretty relevant given some recent papers. That is, like, what if we were training a medical question answering model? Well, if we could have seen the future and we were doing this in 2019, we might have a model that looks something like this, where you pass in a couple different questions and it gives you answers. And if you asked, what's the most recent pandemic, say in the US, then it would correctly say it was the swine flu. And same thing for the year of the influenza pandemic, and what's a safe drug for headache is ibuprofen. But when 2020 arrives, it's giving us the same prediction, but now it's of course wrong because it should be predicting COVID. And so what we need in this case is some sort of a model editor that'll make a targeted modification to the pre-trained model's behavior without impacting other things that we don't want it to impact. So a success in this scenario would mean you can still ask, you ask what's the most recent pandemic, and it successfully says COVID, but you can still ask the same questions before and it doesn't update the model's behavior at all. And so what we need for scenarios like this is methods for doing these edits and making these spot fixes on big deployed models without going off and doing all of this really expensive retraining that can fix the problem if you know what data to collect and how to collect better data. But retraining is becoming extremely, extremely expensive, especially as models grow. So model editing is one posed approach where, again, like, we're given some input, and I'll talk more specifics in a minute, but we're given some input and we're given some label correction, and we want to fix the label without impacting other things that we don't like. And this is an increasingly popular problem. So a couple different papers I'll briefly walk through. One strategy to solving this model editing problem is to basically train a hypernetwork that predicts new model weights. And if you have a bunch of training edits that you can, like, train your hypernetwork to give us better weights for the bigger model that fix just this one thing without changing anything else. If you have enough training edits, you can do a pretty good job at this, especially if you have access to the upstream training data for the big model, which is pretty unrealistic. And then you end up making only one edit during deployment, when in practice, we rarely ever only need to make one fix. We're going to need to make lots of fixes if we actually care about having a robustly deployed model. So most of the existing literature fits into this setup, often requiring large amounts of auxiliary data that is often unrealistic in practice, or being very architecture specific, and then only making one edit at the end of the day during deployment. And they show in their works that as soon as you make multiple edits, the performance of the edited model has dropped through the floor and does quite a bad job on the like actually making good predictions on their testing data. So in a recent paper with collaborators here at MIT, I'm going to focus the rest of the talk on this work. We basically proposed the first approach to doing sequential, like lifelong, long-term sequential edits to big pre-trained language models. So we'll talk the rest of the talk. I'll be just talking about natural language processing. But the key points are first, this is the first work to make thousands and thousands of edits during deployment. We go up to about 5,000 edits in our experiments. And then we also present a brand new paradigm for actually fixing these pre-trained models that I think is in itself quite interesting. So since this is a new problem, I think this is a good chance to be a little specific on what we're really trying to do. And so our problem statement is we want to update a model thousands of times in a row based only on singular streaming errors. So an example of this is like if you imagine you're hosting like ChatGPT or something, and lots of people are using it all the time, and you might not be aware, but you can actually provide feedback in the ChatGPT box, or you can go in and type that you didn't like something that it said, and then so if you're maintaining this model, you sort of get sporadic feedback. And over time, it's been used more and more and more. So it's being used really, really fast. We have this high velocity data. It's being used in more and more cases. And so we'd really like to be able to have methods that you can observe a clear problem. We know what it should have said, and then we update the model right away so that fewer people are impacted by a poorly behaving model. So to be more precise about what we're really looking for, there's 4 key goals that we want to achieve in this problem setup. So first off, we want to actually fix the new errors, like switch from swine flu to COVID correctly. Second, when we're doing this in sequential setup, doing many edits one after the other, it shouldn't be that as you make more edits, you forget the old fixes. Like no matter how many edits go between the same question, between the most recent pandemic, it should still not forget that the most recent pandemic is COVID. Ideally, we'd like our fixes to generalize to similar inputs. So in a simple question answering setup, this means rephrasings of the exact same question. We want to be able to, it's kind of a data efficiency problem where we want to be able to take one of those questions and then generalize our fix to the rephrasings of the same question. And then finally, we want to ignore unrelated inputs. So if my model was already correct for some for some inputs, by editing it for a different type of input, we don't want to break its behavior. And so you might think, like, can't we just fine tune to solve this problem? And definitely fine tuning is not a crazy bad solution, but the key problem here is just overfitting, and that we have new errors that show up. And if you just fine tune on the errors, one, if the errors are all coming from certain subgroups, then you're going to really overfit to those subgroups. And then also it's really hard to avoid overfitting on singular errors because we only have one instance that we're trying to train with. Okay, so to solve this problem, we take an adapter-based approach where you might imagine on the left, we have some big pre-trained natural language processing model, which is, you can think of it just as this big stack of layers. Nowadays, the layers are pretty complicated, but it's still just a stack of these different layers. And the editing, we don't touch the model's pre-trained weights at all. And instead, we pick a layer that we want to edit, and we basically have a wrapper that goes around that layer. And there's deferral. So either we trust the model's original pre-trained weights, or we have this grace adapter that's going to modify the transformations between the layers, and we'll do it very targeted just for specific inputs. Okay, so a little more technical details on how we actually implement the method. So we call our method GRACE, for general retrieval adapters, because we're going to be retrieving hidden states from a cache for continual editing. And so if you imagine on the left, we have our big stacked model. We pass in our question, what's the latest pandemic? It gives us swine flu incorrectly. And imagine we've got 2 of these layers, this layer L and layer L+1, and we want to perform editing. So here's the key intuition is each of the layers has its own latent space, and all the transformations between the layers are doing is mapping from one space to the next space. And so if you imagine on the left, we pass latest pandemic, it works its way all through the model. It reaches layer L, and it's this embedding in the space. We pass it to L+1, and then we decode from the rest of that, and out comes our output. So we hypothesized that for some point on the right, we'll be able to decode it to get the right answer, that is COVID. And this is possible through, in language modeling, especially because of tokenization. We can like combine tokens into any words that we want to predict. And so we assume that this exists. And the question is like, how can we actually find the right embedding such that if we had that embedding on the right, it would go and decode correctly. And you can basically just do stochastic gradient descent using the fine tuning laws of the model to just encourage it to predict COVID. And you only have to do it up to this final layer to just learn the right embedding that does to COVID. And then the final component, or not the final component, but next we have to actually make the fix. So we need to do rerouting from the left, from the key, which we'll call a key now because we're going to do it in a code book setup. The key on the left is just the original embedding for the question with the latest pandemic. And for any new embeddings, including this value, this key, any new embeddings in the future that land inside some radius around this key, we're going to map them directly to value on the right. So we don't have to run the model's prediction to actually go to the place that the model predicts, but instead we just look up the next value and basically teleport straight there and decode from there. So we call it a code book because we can think of this as like key value pairs, where the keys are the input hidden states from the previous layer, the values are the new outputs for this layer. And the magic is sort of going to be the epsilon ball, which is like the influence radius around each key that determines how much of the latent space we actually influence with a new key. And the idea here is you can just store these values, the keys and values, over time. It's just stored separately. And then at inference time, you can just, when you get to this layer, just check for a new input if it's within this radius for any key. And if it is, you just snap to the next value. And so this way, we successfully fix errors. But the interesting part is by changing the epsilon value, we can also change how much these fixes generalize. You can imagine that if different questions that mean the exact same thing land close enough together in the latent space, which turns out they sort of do in a surprising number of cases, if that new question that is the same as the old question lands inside the radius, then that one also gets the fix for free. And so this is the way that the edits actually generalize to unseen. And there's a trade-off here in that, like, if the epsilon gets really big, then lots of new inputs get snapped to this word COVID, and that's not going to be the right answer to many questions. So we sort of want to keep them as small as possible. But what's really nice here is that we directly ignore unrelated inputs because there's this like discrete search going on. It's like we're like discretely segmenting part of the hidden space. And so anything outside of that is just whatever the model originally would have predicted. So we very successfully ignore unrelated inputs. So this is how to do one edit using our method, but ideally we want to do thousands and thousands of edits in a row. And so it sort of turns into a codebook maintenance problem. Like how can we keep a small codebook? But first, what would it look like to just do it thousands of times in a row? Well, you can imagine that if you keep passing different questions in that you'd like to fix the answers to, you can sort of just keep filling up this codebook that's full of these transformations, these cached transformations. But the problem is, when we ideally want the codebook to avoid simply memorizing every single input. And instead, we want to also promote generalizations that our codebook doesn't just memorize absolutely forever. Because again, like this is basically a data efficiency problem where we want one edit, we want to take one new error and have it generalized to some degree to future error, to avoid future errors. So it turns out a pretty simple codebook maintenance strategy is surprisingly effective. So first we check for a new input. Instead of just always adding keys, I guess I should step back too and say, if we just keep trying to add keys forever, eventually they're going to start overlapping with each other, right? And then it's not clear what to do because the discrete segments of the latent space, we don't want them to overlap because they should mean different things. And so to avoid this, we basically start with this process on the right, where we check for a new error, is it near any existing keys? And if it's not, then great. It's off on its own. We know what to do. We can just create a new key and we're good to go. But if it is close by to any existing key, then we have to do another check where first we see, does the value of the neighboring key agree or disagree with the label? So if it's a slightly different rephrasing of the question, like what's the latest pandemic, and it lands sort of outside the existing key, that means that both of those keys would sit next to each other. If we created a new one, both of the keys would sit next together and have the same value. They should both be predicting COVID. So actually the other case first is if they disagree. So like we've got an existing ball like that goes all points to COVID. If they disagree, that means there's something that's close by that shouldn't go to COVID, but they're overlapping. The pretty simple fix is we just shrink the influence of the existing key down because it was too big. It was covering some space that it shouldn't cover. And then we initialize a new key that has a smaller epsilon radius just so that they're like just barely touching. And the case I was describing before, if they do agree, then all we do is we expand the existing key, right? Because like we're saying the key that points to COVID was right next to one that should also point to COVID. So we just expand it and cover it. So that's the way that we avoid just creating new keys and values all the time forever. Okay, and so this way, the codebook actually adapts to the distribution of the edits as they arrive. So you could imagine if you have some portion of your latent space where lots of different edits all appear and they all have different labels, you will end up having a bunch of keys that are all closely packed together with smaller influence radiuses. Whereas in emptier areas, you might end up having slightly bigger epsilons, like bigger influences of the existing keys if the semantically equivalent inputs are landing out in that emptier space. Okay, so very brief implementation detail. The method, this approach works both for encoder-decoder models, like BERT or T5 or something, and it also works for decoder-only models. So if you imagine we're trying to do some sort of language modeling task where you like fill in the masks, we find that on the left, when we're using these encoder-decoder models, if we pass in the blue key and we look up a purple value, it actually works pretty well to just broadcast that value. And this depends on the task, but it's really good for like classification tasks, where you just broadcast the whole value. And it's basically a shortcut for the key value to have heavy control over the model's predictions. And you can learn values really fast. It's kind of unsatisfying, at least I find it kind of unsatisfying conceptually to just like replace all of the representations for all of your tokens with the same value. But it works really, really well, especially in classification. But in decoder-only models, it's a little bit more intuitive that it works quite well to just take the key, look up one value for that existing, just the exact same token at the next layer, and then just keep running everything as normal. And that also works. Okay, so moving on to experiments. Actually, I can take a pause there if there are any questions.
Sure, I can ask one question. If I understand correctly, so you're basically you're learning a new transformation to correct an error. So there is a transformation function which needs to be, I'm assuming you use the erroneous cases to fine tune the weights of that mapping function. But it doesn't change the size of the model because essentially once you have done this mapping, you just keep it as a code book separately. So model size remains the same. Or do you think it like the model size changes if you're doing this on a continuous basis?
Yeah, you're right that the model size definitely doesn't change, and that is because we have the code book separate. I think in practice it is similar to just increasing the size of the model. I mean, we are just using a cache. So if you think about what parameters are actually used at inference time, you're not really increasing the number of parameters that the model has, or you're only increasing it by the the size of the number of keys you have, and then the value that actually gets used, or maybe even just the value that gets used counts. But yeah, so the caching does take up memory, but overall it's a very small amount compared to the big model.
And just like one error is enough to figure out that mapping function. Like,
yes, because
example of COVID, so you have that one error, right, that you want to fix. So you would be able to figure out that one function that would map the question to, instead of swine flu, to COVID.
Yeah, so what's nice is we don't really have to learn the mapping function so much. We just have to learn the value on the right. Like, what is the value that would decode to that? And then it's just a lookup. It's not actually like a transformation of the input to the output. It's just like for some key, can I just avoid using the real transformation learned by the model and just look up a better answer according to that layer?
And you know that better answer because you have the fix to that error, right? You not only you know that this answer is being this question is being answered incorrectly, like swine flu is incorrect, but you also know that the answer should be over. So that's how you know. So that's what you put it. Okay.
Yes. You have to know what answer you're trying to make the model say for this one. For the model editing setup. Finding the right answers is highly non-trivial, and some cases it's easier or harder than others. For instance, this project was motivated by our observations of the bias that was coming out of GPT-3 when I was doing experiments with Microsoft, and we tried to start with that and coming up with like what the model should have said about a specific population. Like it's not actually a good match for this problem setup so far.
The other question is that you mentioned remember old fixes, right? That was one of the properties. Do you see, like, if you keep it's supposed to be lifelong editing, so for how long it should keep remembering, because at some point COVID is going to be the wrong answer. Swine flu is wrong right now, but after the next pandemic, whenever that is, that's going to be the, so how long do you think, like, how do you see that this, like, fixing the fix would be taken care of in your model?
I think this is actually one of the superpowers of the method, in that we know when we have the code book, we know which values go with which labels. So for instance, if we wanted to say all of our labels that are pointing to COVID or something, maybe we want to go through and check what questions point to those and maybe just drop those entries from the code book. We have the power to do so. Whereas if we want them to persist forever, you could just leave them in your code book. At some point, maybe your code book gets way too big, maybe your latent space gets like way too crowded. And so I think there's a lot of room to be very intelligent about going back and restructuring the code books that you have based on other sources of data, or maybe just looking back at the historical data. Right now, we're only working on the streaming setup, and not thinking about that just yet. But that's a great question.
Thank you.
All right, so I'll keep going for experiments then. And I already want to. Sorry,
I think Nandita, you had a question.
Okay,
sure. I had a question, but I can ask later if you want.
If we're paused now, you can just go ahead.
Oh, okay, sure. So I guess if you go back one slide where you're talking about how you're actually using, actually maybe one more, where you're talking about the epsilon balls. That's that one. So I found this approach super interesting because now it looks like the radius or the radius of the ball is kind of essentially determining like what amount should each thing change. But I had a question where, let's say the first fix, like you want to shrink the ball size, but then the next fix makes the ball size expand. So which means that the previous errors fix is actually now almost forgotten, or like it's kind of right. So how do you tackle that?
That's a great question. That's a very reasonable question. So we sort of just assume for now, we assume a recency bias that's like, if we're adding a new fix, it's most important to fix it. Like every time we fix, and we have this criteria throughout the experiments, it's like every time we try to fix the model, we have to fix the model. You have to actually change the model's outputs. And if in order to do that, you have to influence previous edits by shrinking or expanding the ball in some way that you shouldn't have, we say like, okay, we fixed the new error. And I think there's a couple of directions to improving that. One would be, of course, like cache the errors as well. And every once in a while figure out that like if you had clusters of the same answer and have edits in between or something, like it's probably fine to sacrifice some things sometimes to have a really a much more reasonable code book. But yeah, I think the recency bias, it's not a recency bias, but like the recency assumption is saving us in this case. But that is why even in our experiments, I mean, you can see we don't just remember all previous fixes forever unless your epsilon balls are like really tiny. And so finding a trade-off between how big the epsilon ball is and how much memory you like, how many previous fixes you forget is like, it's very real trade-off.
Got it. And I guess just one quick clarification. So In these models, like either the encoder decoder or the decoder models, do you assume that like the latent space, like a point in the latent space corresponds to like the token, or do you assume it to be like a bag of token, like a sentence? So for instance, in the NLP case, like do we interpret each point in the latent space as being equivalent of a word or more of a sentence or a paragraph? Like because I can imagine the fix like that we want to do might kind of depend on this aspect. So
absolutely, yeah, absolutely. This is also a great question. For the sequence, and the answer depends on the task. Right. So for sequence classification, for instance, where we have, I think we did it with a BERT model, where we have some classification token, whatever token that is, we assume that's the sentence representation that we want to be editing. And then even within that, you can choose what layer you want to perform the edits on, and that also has a big impact. For something like language generation from an autoregressive decoder, it starts to get even more complicated, where do you check every single word that you do, like and then only replace just for one token? Like, I think in that case, thinking of it word by word makes a lot more sense. Whereas for something like sentence classification or even question answering, just grabbing the final embedding and saying this is our representation of the whole sentence seems to be fine. But I think it's more of a conceptual question than a practical question, because like I mentioned before, like on one hand is what do we say is the key that we're looking up, and then what do we actually replace? And you can be like, and then it even changes the interpretation even more. Like if you're replacing the representation for every single token to encourage the whole model to very confidently predict one class, that is even different. Yeah, that's a great question.
Thank you. Yeah.
All right, so with that, maybe I'll move on to talk experiments. So overall, we focused a lot on trying to come up with scenarios where we fix real mistakes made by models. This is kind of in contrast to previous works which largely do synthetic edits. They like invent they like try to take a real model and then edit it to make random predictions. We're trying to do something different, where we actually have a realistic scenario, we look for mistakes, and then we actually fix them. And so assume that we're given some big pre-trained NLP model. We then go off and acquire a set of potential edits from a new data set that the model wasn't trained on. So if it's like question answering, we might have, the model might be trained on some QA data set, and then we're testing it on a new, more recent QA data set. And then we take the model, we take the new edit data set, we run the edits one by one through the model. And then every single time the model is wrong, we then edit it using Grace and our compared methods. And then we evaluate that new edited model on 3 key metrics. So first we check, was it successful? Like, did it fix the error? Second, we take the new edited model and check on the original, like that new edited model, its performance on the original test set from the pre-trained model. And then we also check that new edited model's success on all of the previous edits that we've passed up to a certain point. Yeah, and so again, previous works, they just make one edit. We're doing it for thousands of edits. And also their edits are so far almost entirely synthetic. And so as an illustrative example, first, before diving in even here, as an illustrative example, we show if you pre-train just a small, fully connected network, you can see on the left is our upstream training data. We've got 2 clusters of data. It's like red versus blue. If you train a model, the decision boundary is going to be straight in the middle. Then if some edits arrive on the left, there's like a little cluster of blue that we didn't see during training, but the label should be flipped all within there. In section C, you can see obviously the pre-trained model in this case predicts wrong for all of them, but using Grace, you can fix all of these predictions using only one key, because we just have like a little key with a radius around this point. We do it in the latent space, but the effect is pretty clear that we could make this targeted fix. Okay, and then so for our main results, we basically show a couple things. The overall punchline being that Grace indeed successfully corrects thousands of errors sequentially. But we find that past work, which only targets tens of edits, we find that it forgets surprisingly quickly. And on top of that, they rely heavily on using auxiliary information, like having a data set filled with rephrasings of your edits and stuff, which is pretty unrealistic, I think, in many scenarios. So you can see on the right, We do this for 2 tasks, and I'm going to show a sneak preview of another task that's not in the paper yet, but will be in the paper soon. So first one is context-free QA, where there's no like document you're asking questions about. It's just a straight up question, like who is the president, and then the answer, and there's no context at all. We can see we've got these 4 key baselines from ACL and iClear and ICML. We basically find on this edit score, which is just the average between the upstream testing accuracy of the edited model at each of the steps, and the online accuracy, which is just remembering the historical edits. This is a pretty standard score, but if you're interested, you can check the paper. We've got the raw values as well. And basically for each of these models, we see as it goes to the right, this is the number of streamed inputs that get passed in and edited. And we can see that in both of these cases, Grace substantially outperforms the alternatives by catastrophically forgetting less. And importantly, we do this without we assume no access to auxiliary information. This is only using the test time errors, which I think is pretty exciting. And then I'll show in a couple slides that we also show that our edits indeed generalize to holdout edit sets. We focus on the rest of the experiments on context-free QA, or the next batch on context-free QA. So then we wanted to dig in a little bit deeper, just go layer by layer and see how are the trade-offs going between memorization and generalization of our errors, or of our Grace editors. And we basically find a couple key things. So first off, choosing which layer you edit actually matters quite a bit in terms of the trade-offs between the 2 key metrics, one being remembering upstream data, and 2, successfully remembering your edits. Right? And so we overall find that editing later layers, like higher layers in the model, it's easier to forget your edits, but you do a better job of remembering the upstream data. And inversely, you can edit earlier layers that successfully remember your old edits, but then it deletes the information from the upstream information. And then we also see that choosing epsilon matters. And I should say, like, there's only one hyperparameter in the method, and that is what is the initial epsilon you start with. And so if you start with really tiny epsilons, you're going to always remember, but your codebook is just going to grow because it's just never going to hit the same edits twice, and it's like just a pure lookup table. And so so obviously smaller epsilons always memorize. They successfully remember old edits. They successfully remember the upstream, but they don't generalize at all because the 2, like rephrasings, in this case, we're looking at rephrasings of the same question. They don't land in the same keys ever. And big epsilons indeed, like they indeed do that generalization, but they screw up the latent space too much. So fortunately, you can get good balances between these goals by just picking the right layer and picking the right epsilon. Okay, so we also looked at a holdout set of edits that the model had never seen. There are just 5,000 rephrasings at test time, and we find that we can get the F1 score up to around 0.84, I think, by choosing these things correctly, which does indeed show like surprising generalization capabilities in some cases, though choosing the right values might not be that easy in all tasks. And then finally, just some codebook stats, where we're just looking at the number of edits that are actually made. And so you can see at the top, when epsilon is small and we have very, very small influence, you just cache like every single mistake, right? And as epsilon gets bigger, you stop caching all of them, but there's sort of a trade-off. But excitingly, either way, the Grace, like the codebook size actually saturates, and that's in part due to like the number of potential questions, or the number of potential right answers, because you can't have fewer codebook entries than you have like unique answers. And so at some point, like this is actually like really good news for our method that we saturate earlier than that. Okay, and then finally, I want to just wrap up the experiments part with a bit of a sneak preview, because we've also done some experiments on editing GPT models with Grace. So in the spirit of a seminar, these are like exciting and new and possibly prone to change, but I'm at least excited about the findings so far. So we basically are editing the GPT-2 extra large model to try and encourage it to hallucinate less. So there's a really cool paper recently where the authors actually take GPT-3, have it generate a bunch of sentences, and then annotate which sentences are right, like which sentences are hallucinations, and which ones are not, because language models hallucinating is a big problem. And so we want to see if Grace can actually help us train a model to not hallucinate if you know what it should have said instead. And so there's this cool data set where the authors actually annotated a bunch of sentences, and we're training a GPT-2 extra large model to mimic the behavior of the original GPT-3 model that did that just for this data set. Those experiments aren't quite finished yet, but for the non-mimic version where we're just updating GPT-2, we're starting to get some exciting results. But first, an example of what this looks like is like, if we're asking the model to generate, here's a Wikipedia passage about a certain thing, we know what the Wikipedia sentence, the Wikipedia response should have been. But we also know that the model didn't do that. And so just as a really quick example, you can see this Rome paper from NeurIPS last year. When we try to get the desired response on the right, it gives us some stuff that's kind of reasonable, but overall like has some inaccurate data that's in there and also starts repeating nonsense. And unfortunately, like this method actually just updates the real weights of the model. So now by making this change, you've sort of screwed up a lot of potential things. I'll show more extensive experiments in a minute. And you can see that Grace successfully, just by learning one value, can successfully like basically compress the future sentence that you care about into one value that you learned, which is pretty darn exciting. Okay, and here's some exciting, very new, but ongoing experiments where we basically we're looking at the perplexity of the model after editing over time. So we do this for 500 or about 500 edits, and all of the values, this is all the perplexity differences. So we want them to be on the left, we want them to be down. Overall, we want all of the metrics to be down as far as possible. And so I also want to say, like, we added a bunch of baselines down here for this experiment. But overall, we find some exciting things so far. That is, first off, of course, like as expected, the Grace edited models don't touch the upstream perplexity at all. Whereas the other models have strong influence on what the model actually thinks is a reasonable sentence. Again, as expected, like we're looking at what are the sentences that the model was already right on. Hopefully Grace leaves them intact and it successfully does that. Grace successfully so far remembers previous edits. And so right now it's competitive with continual learning approaches, which is actually really exciting because this is for a GPT-2 model that's really bad at this task. So it's successfully remembering good things, whereas the fine-tuning methods are actually just fine-tuning the model on this data set and overall just becoming better at predicting words in this data set. And then again, Grace successfully makes the immediate edits, which is pretty cool. Okay, so finally wrapping up, contributions. First, this is the first sequential editor, though there's a recent paper that came out that also is doing in a slightly different sequential editing setup, but ours is architecture agnostic. We're only using errors, and we don't have access to any extra data or any pre-training, nothing. It's just all during deployment, one hyperparameter. And it's also the distance search in the latent space is a very promising approach for editing, and it's also new for how to modify the behavior of these models. And some exciting next steps. So the motivating example, like medical question answering, is now in the news a lot more, and looks like it's actually kind of coming, whether you like it or not. And so there's been a big batch of recent interesting papers talking about these sort of chatbots for medicine, but I'm pretty surprised. But I feel that there's not nearly enough tools for actually updating their knowledge. And in medicine, obviously new knowledge comes around all the time, or new bad behaviors are identified all the time. But if you went and pre-trained one giant model and you're a company, updating that model is not necessarily easy, cheap, or even incentivized. And so we need these sort of approaches. I think these editing, this editing direction has a good potential to personalize your interactions with these big models eventually, and hopefully decentralize some of the power that is sort of baked into these large models. Some other exciting next steps, just sort of brainstorming, is this is sort of a continual method for adding new knowledge, but if you have we should have more continual methods with adding and removing old knowledge, so sort of continually learning and unlearning simultaneously. I think we'll probably get much more robust editing performance. Pre-trained models are not just for language, even though I talked all about language today. We're starting to see lots of pre-trained models, especially there's just very exciting stuff on like EHR pre-trained models, which is a conversation in and of itself, but these sort of editing techniques need to be general, and Grace is general. And so we're working on a couple follow-up papers on applying it to different settings. And then also I think different styles of editing should appear. I mean, it should be like concept-based editing where we know that our model is making this sort of categorical mistake or mistakes for this sort of input, maybe almost prototypical. How do you fix it once you know some information about some latent concept? And then finally, looking into the future a little bit, the future of lifelong model maintenance, and the grand question being, how can we maintain deployed models for longer, or even ideally, of course, like improve their behavior throughout deployment. So first off, I think we need more methods for maintaining multimodal models, like I just mentioned. I mean, some of the stuff that I'm excited about is in the time series representation learning space, especially from heterogeneous data sources. More than just accuracy shifts over time. So if you want to make your model more fair or more interpretable or abide by some new privacy constraints, I think there's a big need for more tools for adapting to these sort of like non-accuracy style shifts in real time. And then finally, we need more tools for actually identifying, categorizing, and explaining these root causes of failure modes, and figuring out how can we actually successfully acquire the corrections to the model that would be helpful, and a more active data acquisition process for coming up with ways to fix these pre-trained models and make both these targeted fixes or even use small amounts of data to make bigger, broader fixes. And so with that, I want to wrap up. Before I take questions, I want to take some time to make a couple announcements in case anybody's interested. We have a ICML workshop this year on challenges in deployable generative AI. I'm really hoping to get some great health or medicine focused papers. Also, I'm, as was mentioned before, I'm the general chair for Machine Learning for Health Symposium. It's co-located with NeurIPS this year in New Orleans. It's like the day before NeurIPS, and it's very exciting. So please consider submitting papers and attending. Also starting a faculty position at the University of Virginia. So if you want to work with me on any of these topics, I'm definitely, or if you know anybody who might, definitely be looking for students to work with over the next couple of years. And with that, I'm happy to take any questions.
Thank you very much, Tom, for this interesting talk and some very interesting future directions, since I work a lot on this multimodal fusion model. So I'm very interested to see how would you identify like which modality is the reason for this error and how do you fix that before the fusion or after the fusion. So I guess it's going to be very interesting. So before I open the floor for questions, I just have like one little question about your experiments. When you say hold out edits, what exactly do you mean by that? Like it's the type of error that you have never corrected, or it's just another variation of it's another variation of the question that you haven't shown the model during the training part. So what exactly is the hold out edit?
That's a great question. Yeah, so all of the, I should have been clear. So all of the ablation questions at the end, including the holdout, that's all for the QA task. And for the QA task, we have rephrasings of the same questions. So it's like you edit on these, I think we edit on 5,000 samples of 500 questions, and then test on another 5,000 samples of those like general questions. So they're rephrasings of questions it's seen before.
Rephrasings of questions.
Yeah,
that makes sense.
But it's never seen that phrasing of it.
That phrase before. So it can test out the generalization part of your method. Exactly. And another question, it's a hyperparameter. So how do you generally like start setting the epsilon parameter? It's a hyperparameter. What value would you start with? It also is task dependent in your experience. Like for question answering, you would start with a larger epsilon, or maybe some other task for a smaller epsilon, or it's just, or you don't think it's very task dependent too?
It's probably, so I won't have a concrete answer beyond it's probably task dependent. I have to go back and it's in the paper for what epsilons we chose. We did use the same range of epsilons in the experiments, which was from like, I think we went as small as 0.1 up to as big as like 8. And we found that most of the interesting behavior was between like 1 and 4, if I remember correctly. I think tuning that parameter is not necessarily trivial because you're like assuming you're really doing it in a full deployment scenario. But I think with access to even a small validation set of any sort of representative data, I think you could come up with some reasonable estimate just based on how far apart all of your instances are that you've seen. I don't know exactly, like I don't have a number or an equation to tell you, but I think that would be very helpful. I also think that in practice, as you're like building up the stream, as you go back and look at the previous ones, I think it's probably pretty reasonable to, as you reinitialize the code base, also come up with, or sorry, the code book, to reinitialize the code book, also come up with a reasonable estimate for what you think. Like pick a reasonable epsilon based on that.
Thank you very much. I think Nandita has a question.
Oh, yeah, I think this was an amazing talk, and I guess I'm also really interested in like model editing. So I guess this is more of a future work plus / your thoughts or brainstorming kind of a question. So I feel like Grace can also serve as a really good like opening up the black box kind of a thing, because now you have some methods for visual, like, or maybe just understanding the latent space better. So have you given some thought about how you can, maybe pair this up with visualization techniques to kind of like identify like cool things in the latent space, and then like maybe use that to guide setting the hyperparameter for epsilon and like lots of interesting things in that space. So just wanted to hear
this is a great question. I have absolutely thought of it, but not in any concrete detail. Only that it is. I think it's I can only say I agree. I definitely agree. It's something we thought about analyzing the code books and what are the different ways to analyze the code books. One thing we're thinking about now is once you have the code book, if you want to know more about either the latent space or the code book, there are methods you can use to say, take your inputs, perform some different perturbations and see whether or not they land in the same, land on the same keys as the original one, or even work backwards and say, well, what are the topics this key is actually representing? There are some exciting methods for taking points in the latent spaces of these large language models, for example, and working our way backwards into the feature space to say what sort of inputs would actually land there. I think that definitely opens doors to better understanding the inner workings of the language models. I think also having the code book to inspect in general is a promising direction, because I think it's a personal, again, I said it before, but I think there's good implications for personalization, where you could have your own code book that modifies the behavior of your model in the way you like, and somebody else could have a different one. And with this sort of plug and play style, I think there's good potential on that front as well.
Awesome. On the flip side, I also I feel like Grace also makes it pretty easy for adversarial players to kind of if you have a pre-trained model, now you can make it bad on purpose. And so have any thoughts on how, how can we avoid that? Is there a safety thing that we can say that, not all fixes need to be, is it more you just need a human in the loop to make sure this doesn't happen? Or is there something that we can do algorithmically to kind of prevent that?
Yeah, I think that's a great question. I think there's two components of the answer. It sort of has to do with two categories of misbehavior on the adversary's side. So on one hand, if they're trying to convince your model to do, for instance, when we were working on GPT-3, it was generating hate speech. If you're trying to if somebody convinces the model to generate explicit hate speech, that is clearly hate speech based off of racial slurs or these sorts of things, then it's nice if they do it with Grace, because you can just take a look at what the values are decoding into and see what is the sort of stuff that this value is encouraging the model to do. And we have a very concrete way of looking at how is the model being modified. And so in that case, I think it's feasible to just try and detect those sorts of things, especially if all of their edits are getting passed through some code book that you could actually just inspect. On the other side, it's closer to my previous work in hate speech, which is implicit hate speech, which is really, really hard to detect at scale. And if you read it, most people would agree for most cases when you see what is hate speech and what is not hate speech, but there's not even clear consensus, and it depends. It's so much more contextual. And so if someone is succeeding to make really subtle changes, I don't know. I don't know how they would do it. I would imagine if you're in an environment where somebody can use a Grace codebook to edit, they also could just fine tune the model or do any other do other sorts of updates to the model as well. In which case I think this question actually is much broader than whether or not Grace is susceptible to it. But I think having the codebook to inspect is actually a benefit in this case. That we haven't investigated that at all. We've definitely thought about. I mean, some of the original ideas of the project, like, can you find regions in the latent space where certain biases are sort of getting funneled and make generalizable edits? And we haven't actually checked that, but the answer is probably no. But it would be good to check, because if it is, then this is really great for that as well.
Yeah, thank you.
Yeah, I think I agree with you that a code book-based model, at least, it'll be easier to fix compared to the ones which are doing fine-tuning of the whole model. Right? If something has changed there, there isn't really a way to go back. But if you have a code book, maybe you can just edit the code book.
Exactly.
So that's very interesting. Okay,
yeah.
So I think we are right on time. So you're okay with us uploading this video on YouTube?
Yep, of course.
Okay. Thank you very much, Tom, for this interesting talk. We'll put up the video on the YouTube and we'll share the link.